Welcome to the third and final video in a three-part series over ionic bonds. In this video, we will be discussing the structure of ionic solids. If this is the first video in this three-part series you are watching, and you feel at any point confused, I recommend watching parts 1 and 2 over ionic bonds on my channel first. In this video, we will begin by analyzing the crystal lattice structure of ionic solids. I will then lecture on how this structure results in the properties of ionic solids. And finally, we will use Coulomb's law to compare the structures of different ionic solids. Let's begin. We know that an ionic bond commonly forms between a nonmetal and a metal. And this is due to the fact that there is a very large difference in electronegativity between these two atoms. This allows for the full transference of a valence electron and the formation of a cation and anion. The electrostatic attraction between these two ions is immense, and because of this, they form a very strong bond, an ionic bond. When we have many of these electrostatic attractions near one another, they like to arrange themselves in a very neat geometric pattern, the one you're looking at right now. This is what we call the crystal lattice structure of ionic solids. You need to be familiar with the pattern we can see in this crystal. Let's say that these purple blobs are negative anions, and these yellow blobs are positive cations. As you can see, in the crystal lattice structure, cations and anions are neatly ordered in repeating row of anion, cation, anion, cation, etc. We refer to this as the repeating 3D lattice. Each one of these cations, let's say this one, is in contact with only anions. And each one of these anions, such as this one, is in contact only with cations. The number of oppositely charged ions surrounding a central ion is known as its coordination number. The coordination number of this ionic solid would be 6. Because let's say we choose this anion, it's touching one cation here, a second, a third, a fourth. It would be touching one hidden behind here, a fifth. And then, of course, if we had finished the structure, there would be one in front of it here, a sixth. So again, this ionic solid has a coordination number of 6. And that right there is pretty much what you need to know about how the structure of ionic solids actually looks. As with other sciences, one of the basic rules in chemistry is that the shape of a substance determines its function. And so let's see how the shape of crystal lattices result in the properties of ionic solids. And starting with the most obvious, the state that we find them in. At standard temperature and pressure, the vast majority of ionic compounds exist as solid crystalline structures, which we commonly refer to as crystals. They are solids at room temperature. Know that. Another property you must be familiar with is the high melting and boiling points of ionic solids. This is just due to the fact that, as the strength of the electrostatic attractions between atoms, aka the strength of the bond, increases, so does the melting and boiling points of the compound. The stronger the forces holding atoms together, the higher the melting and boiling points. That's pretty much what you gotta know. Due to the polar charges found in ionic bonds, negative oxygen atoms in water attract to cations, and the positive hydrogen atoms in water attract to anions, which I've drawn below. Just to point it out for you, these positive hydrogens are attracting to this negative anion, and these negative oxygens are attracting to this positive cation. These attractions by the water molecules will rip the structure apart into the individual anions and cations. This is why ionic compounds are generally soluble in water, because water molecules can rip them into their anions and cations. Let's look at the electric conductivity of ionic solids. The conductivity of electricity is due to the movement of charged particles. This is why metals are such good conductors, because of their delocalized sea of electrons, charged particles which can easily move. When in their solid state, however, ionic bonds do not allow for the movement of any charged particles, since their ions are held in very strong bonds with one another. Because of this, we say that they are not conductile. However, remember and think back to how I just showed you that water molecules can rip apart ionic solids into their individual cations and anions. When this happens, if we were to take an ionic solid and dissolve it in water, the mixture would now contain a bunch of tiny individual free-floating cations and anions, which are charged particles. These free-floating ions would be able to conduct electricity. You need to know this. When in their solid structure, charged particles in ionic solids cannot move, and we say that they are not conductive. When dissolved in a mixture, the ions can now move, and so the mixture becomes conductive. This is why, if you dump a ton of salt into water, it will conduct electricity. The last property we will look at for ionic solids are their hardness and brittleness. Again, ionic compounds are solid at standard temperature and pressure, and we can refer to them as quite strong. However, what would happen if we were to hit salt with a hammer? It would break into 1,000 little pieces and go everywhere. That's the brittleness of ionic solids, and it's due to the way the crystal lattice structure is set up. Imagine here in this circle that the black circles represent anions, while the red circles represent cations. Now imagine that I take a hammer and hit this ionic solid and force it to move down. What will happen is that part of the crystal will shift. And what do we now see happening? Well, at this point, right here, we see that two cations are touching each other. And here, we see that two anions are touching each other. And so what happens if atoms of the same charge begin touching each other? They will repel. They will repel the other away from themselves. And so the crystal lattice breaks. That's why we refer to ionic solids as brittle. Because if we were to apply a force on them, their anions and cations would shift and begin repelling one another. And so they would shatter into thousands of little pieces. So, these 5 properties that I've written down here are all ones I think you should be familiar with and probably memorize. To finish off this video, let's now use Coulomb's law, which I've written below, to compare the properties of different ionic solids. Remember that Coulomb's law pretty much states that F, the force of attraction between two particles, is approximately equal to Q, the charge of the first particle, times Q2, the charge of the second particle, divided by R squared, the distance between the two particles. When comparing ionic solids using Coulomb's law, there are 2 factors we need to keep in mind. Number 1, the charges of each ion, and 2, in the event that these charges are the same, the ionic radii of the atom. For instance, which of the following compounds has a higher melting point? NaCl or CaO? Well, let's remember our 2 things in mind. First of all, let's figure out the charges of each of these ions. Navigating to the periodic table, we see that sodium is in the first group, therefore it has a charge of +1, and chlorine is in the 17th group, therefore it has a charge of -1. Calcium, however, is in the second group, and so it will have a charge of +2, and oxygen is in the 16th group, so it will have a charge of -2. As we can see in Coulomb's law, as the charge of the particles increases, then the force of attraction between these 2 compounds must also increase. Therefore, because CaO has larger charges for each ion, CaO will have a higher melting point than NaCl. For our second example, which of the following has a higher melting point? NaCl or NaF? This time, the charges of each ion are the same. They are both plus or minus 1 respectively. So we need to go to step 2. We need to look at the atomic radii. We know that the fluorine atom is smaller than the chlorine atom. This means that there is less distance between the 2 atoms in NaF than there is in NaCl. According to Coulomb's law, as the distance between 2 particles decreases, then the force of attraction must increase. Therefore, NaF will have a higher melting point than NaCl because its force of attraction is stronger. So, just to recap this last part of the video, when comparing 2 ionic solids using Coulomb's law, you need to compare the charges of the ions, and if they are the same, then you can compare the atomic radii. Congratulations! You now know the crystal structure that ionic solids form, the properties that this structure results in, and how to compare the properties of different structures to one another using Coulomb's law. I know that this was a lot of information to take in at once. If you are struggling with any of this, try rewatching parts of the video. If it's still not making sense, just take a break and come back after. If you have any questions, please leave them in the comments. Thank you for watching.